In the construction of algebraic geometric codes, the function fields with low genus and a large number of the rational places or the rational points when we consider the curve are going to be interested in this. So for this purpose, the second case, I want to explain what kind of information do we have for the genus 2 case. And indeed, we show them as a spatial type of function fields that are called hyperelliptic. And indeed, we define them as a function field of genus at least 2 and as field extension of some transcendental x. Which has a pole at the place at infinity. And indeed, when I explained the hyperelliptic function fields, what I didn't give was, indeed, what I didn't explain was their explicit equation form. Indeed, if you check the proposition 6.2.3 from Stettenot, you will see that the hyperelliptic function field of genus G of genus G, let me write it this way. Genus G can be written as a function field of K of xy. Here, x and y has algebraic relation as y square is equal to f of x. Like in the elliptic case, here f of x denotes the square free and of degree 2 plus 1 or 2g plus 1 or 2g plus 2 with genus G. And of course, when we compare to elliptic function fields, the situation in the hyperelliptic case is a bit more complicated, but still certain answers are possible, like the number of the rational places. And indeed, Jean-Pierre Serre explained that if Q is a prime power, Q is an even power of a prime, then the number of the rational places is equal to Q plus 1 plus 4 times square root of Q, but here Q is different from 4 and 9. And when Q is equal to 4, it is given as 10, and when Q is equal to 9, it is computed as 20. And if you consider the Saville bound, so n minus q plus 1, absolute value of n minus q plus 1, it's going to be less than or equal to 2g plus square root of q. Indeed, since the genus is 2, the maximum number of the rational places is going to be 4 square root of q plus 1. So when we plug in q equal to 4, in this case, n is 13, so this is not, we are not going to get the maximum number of, the maximum of the, it's not going to be maximal in this sense, it's not going to attain the upper bound of the Saville bound. And like in the, if we consider the q as 9, indeed the Saville bound gives us 22, but in this case we get 20, and this case is not also maximal in this sense. But when Q is an odd power of a prime, we need to indeed, it was divided by certain case. It was analyzed by a certain case. So if Q is an odd power of a prime P, then first we introduce a notion what is called a spatial. Q is called spatial if P divides the floor of 2 times square root of Q, or if there's exists the integer such that we can write Q as a squared plus a plus 1 or a squared plus a plus 2. And if Q satisfies this one of these properties, so if it is spatial, then the number of the rational places can be computed by these numbers here. We need also, they also consider the conditions like if 2 times square root of Q is minus floor function of 2 times square root of Q is bigger than square root of 5 minus 1 over 2. And let me write it T, and T is less than, strictly less than square root of 5 minus 1 over 2. So it's, as you can see, it's a bit ugly. And when Q is not spatial, so that means when it doesn't satisfy this one of this property, then the number of the rational places is computed as Q plus 1, 2 times 2 square root of the floor function of 2 times square root of Q. And indeed, as an example, if you consider the hyperelliptic function field of genus 2 over F16, the number of the rational places is computed as 33. And indeed, again, von der Veer gave an example by using these parameters. So he considers the D as the sum of the all rational places, which is different from the base point. So that means the possible length is going to be 32, because this, the number of the places also counts the base point. Sum of all rational places which are not base point O or place at infinity. And he considered the divisor G as M times O. O is the place at infinity. Then he produces a kind of family of linear codes of the fixed length 32 and dimension 33 minus M, and minimum distance, which is denoted by dm, and it is computed as M minus 2 when M is strictly bigger than 3 or less than or equal to 31, but which cannot be 5. and D3 S2 and D5 S4. And the general question for the maximum possible length for a code, so relating the maximum possible number of the rational places for the genus 1 and genus 2, in general, investigated by Manuela. And one of the things I also want to point out, so the Riemann-Roch space, and in this case, it is of course a bit more difficult if compared to Riemann-Roch spaces in the elliptic function field we consider. But still, in the literature, you may come across some spatial forms of the Riemann-Roch spaces for the divisors, for the Riemann-Roch space of the divisors in this form, for the hyperelliptic function fields.